a Portland Community College mathematics telecourse. A course in arithmetic review, produced at Portland Community College. This lesson will be short and easy. It will also serve to illustrate why decimals were invented in the first place, and that is to allow us to work with mixed numbers and fractions as though they were simply whole numbers. So the rule for adding decimals is simply this. Decimals can be added just like whole numbers if they are written in vertical columns, if you keep like place values aligned, that is, you line up the decimal points, and you write in extra zeros on the end, it will help you to keep those place values in line. Now this is better illustrated with our example. You might simply recall your elementary school teacher simply saying, keep the decimal points lined up. But implied with that was more than keeping the decimal points lined up, but keeping the like places lined up. Ones places with ones places, tenths with tenths, hundredths with hundredths, ones places with ones places, and tens with tens, ones with one, decimal points lined up, tenths with tenths. Now let's pause there and make a note about this particular number right here, which has no decimal point. Note, all whole numbers do have an implied decimal point, and it's implied to always be on the right end. So really, whole numbers have decimal points. It's just that we normally don't write it. But logically, it is there, and always to the right. Be very careful. A few people have, for some reason, put it in front. It's always behind, always at the right, never an exception. So in our example, this 3 does have a decimal point, and we have all of our decimal points in a line, which will be the line of the decimal point for the answer. Now, if it will help you, because this might look scraggly, you might want to append zeros on the end to remind myself that all the tenths are lined up, all the hundredths are lined up, and so on with messier problems. With practice, you won't bother writing these. You can work okay with them as they are. Then at this point, when you've lined up your decimal points, put the decimal point in the same line for the answer, forget that it's even there, and just add as though it's a whole number. So adding this column, we have 5. Adding this column, we have 11, which is 1, carry the 1. Adding this column is 5, and 5 is 10, carry the 1. And 20. So my answer is 20 and 15 hundredths. Simple. Line up the decimal points. Make sure that the places are lined up. Use the zeros on the end if necessary. Then just add as though it's a whole number. Again, first, vertically line up your decimal points. Remembering that whole numbers indeed do have decimal points on the end. Then if it'll help you to keep your places lined up, stick in the zeros, but they're not really necessary. But it is necessary to remember that the decimal point in the answer stays on that line. Now adding the columns, you have 9, 18, carry the 1, 15, 22, and you're done. So it's simply a matter of having the like places in a row. The purpose of the decimal point is to, of course, separate the division between whole numbers and decimals, but also to give us a visual focal point for lining up. Now, with not too much practice, you'll be able to add horizontally as well by first adding the hundredths, which is 9. Then you find the tenths, which is 2, 9, 18. Then you move over to the whole number, which is 9, 15, 22. Carry the 2 to the tens place. There aren't any, so that's it. It actually is easier to line them up vertically, but some people are so good and fast they prefer doing it this way so they don't have to rewrite. But if you make mistakes or if you're a little bit slow, then come back to the vertical approach. Now, frequently you're asked to do something, in this case add, and then round off after you're through. So adding these first by lining up the decimal points, we get this. Adding the place columns, we get 15, carry 1, just like it's a whole number. 6, 8, 12, carry the 1. 9, 14, 16, carry the 1, 2. Double check. 15, carry the 1. 6, 8, 12, carry the 1. 9, 14, 16, carry the 1, 2. Now the instructions were to round to the nearest hundredth, which is here. We look at the digit just before it. It's 5 or more, so that rounds up to 3. And everything else stays the same, and everything behind it gets dropped. So our rounded answer, our approximated answer, is 2.63. See, addition of decimals is really no harder than addition of whole numbers. And of course, the added bonus to decimals is they allowed the structure which permitted engineers to design calculators to do the work for us. So on the calculator, each mark here is a button, including the plus. And of course, when we're all done, we want to know what the whole thing is equal, so we have one last button, equal. So working with calculators, which we have been doing all along, it's just that simple. We simply start hitting those buttons. 4, 8, 5. See, we forgot the decimals, so we clear and go back. 4.85 plus 5.2 plus 0.3 plus, now I could have entered that 0 too and it wouldn't have altered things, 18.9 equals 29.25. Now indeed my answer can be wrong, because interestingly enough, the calculator is very fast, but people who make a mistake by hand will tend to make mistakes more frequently even on a calculator. But a calculator is so fast that the way you check with a calculator is simple. Do it over. Okay, so once again, 4.85 plus 5.2 plus 0.3 plus 18.9 equals 29.25, so we were correct. So always, when using a calculator, do the problem at least twice. It's a decimal system that made the calculator possible, in a sense. With those last few examples, perhaps you can see why our ancestors invented the decimal number to begin with. We found in the last chapter that by adding with fractions is not always an easy task. It was found if we limit ourselves to specialized fractions, that is, those fractions whose denominators are powers of 10, then we could in fact write each of these fractional mixed numbers in a different manner. That is, we could leave the denominators off altogether because the denominators are implied in the decimal place position. Therefore, by using rules we just had, that is a simple rule that if you're going to add decimal numbers, you in effect line up the decimal points of the addends, remembering that with whole numbers, the decimal points to the right end. Also remembering it's not just the decimal points you line up, it's the place values. If you remember all of that, and it's really quite simple, and if you remember that now you keep the answer decimal point along the same line, then you are allowed to forget that these even were fractions and simply add the resulting setup as though it were a whole number. So we simply add this column, which would be 16, add the next column, add the next column, and we're done. And of course, this is the mixed number in fractional form, 10 and 56 100ths, which in fractional form we probably would reduce. But the point is, this is a lot easier this way than this way. And as you'll find in the next few lessons, with fractions, whereas subtraction, multiplication, and division becomes even more complicated, in decimal form, it stays simple. And also, decimal form allows us to do much of our arithmetic on calculators or in computers. So you see, you really begin to appreciate this invention, which, by the way, came rather late in our mathematical evolution. Therefore, I think you'll find this to be a very simple, short lesson. So let's use the remainder of our few moments together to begin to get ready for algebra, as we've been doing from time to time throughout this course. Here we have an algebraic sentence which says some number, and remember that a variable, a letter in algebra, is simply a mark that stands for the phrase some number. So it says some number subtracted by 18.6 is 4.3. And solving the equation means finding the value of the number that variable is temporarily standing for. See, the variable is sort of like a pronoun. It's merely standing for something until you find out what it is. And we learned in a few lessons back that in fact if you're subtracting a number, you undo that subtracting by adding the same amount. So if I'm subtracting 18.6 from anything, then turn around and add 18.6 back on, this addition has just undone this subtraction, and I'm right back to where I started from, which is just the variable. But our rule was in algebra was if you have a mathematical sentence called an equation and you want to add something to the quantity over here, that's okay, providing you add the same amount over here. So now this reads, since this has undone this, that x is this number plus this number. And we can probably add these horizontally. 3 and 6 is 9, decimal point. 4 and 8 is 2, carry the 1, gives me another 2. Or if you wish, as you add to both sides, simply line them up and add that way if that's easier to you. But the main thing to remember are 2 points. Addition undoes subtraction. Second point, you may add anything you want to one side of an algebraic equation, providing you add an equal amount to the other side of the algebraic equation. Let's do another. Let's say that somehow, from some applied situation, you came upon this equation, and for whatever the reason, you need to solve for the variable f. Now, the reason we use different variables, different letters, to stand for the simple phrase some number, is that often it helps us to remember where this came from. It might be that F stands for force. It could be F stands for Fahrenheit. But the point that we need to realize in this simple example is that actually we're trying to isolate the F by itself. And we recall the rule that addition undoes subtraction. And we also recall the rule that whatever I add to one side of an equation, I must add the same amount to the other side of the equation. Therefore, this addition undoes that subtraction, isolating the variable, which is called solving the equation in more advanced algebra. Then adding these two together, we get 69.2. If we wish to check it, this is saying, look, F, which we're claiming is this, subtract 49.5 is this. And subtraction is going to be our next lesson. At that point, we'll find that by doing this, we can check that this is correct. At this point, to check it, we would simply redo our problem to see that we do come up with the same results by adding more carefully a second time. Let's do another one just to emphasize that there's nothing saying the variable has to be on the left side of the equation. It could be on the other side. This could be a situation in which you knew that if you take your tax amount and subtract this amount from it, it might be a refund from an overpayment from the previous years, you should have this amount of money. So the question we want to know is, what was our original tax? So reading this is saying your tax decreased by $596.75 is $6,784. What was the tax in the first place? Well, actually, if we're playing the game of solving algebra, we can forget what this even stood for and where it came from. It's just a matter of isolating that t, and all we have to remember is to undo a subtraction process. We simply add the same amount. And this undoes that, isolating the t, which is what we're trying to do when we solve an algebraic equation. But our addition law of equality says, fine, add anything you want to any side of the equation, providing you add the same amount to the other side of the equation. And of course, here we have to recall from this lesson that the decimal points on the right end, that we are to line up decimal points. We can insert zeros behind the decimal point if we wish. Now adding place value to like place value. We have that my original tax is $7,380.75. Now, let me use an especially simple problem to illustrate how algebra is going to work in the future. Quite frequently in reality, you can describe a situation, something that's occurring, where something in that situation is not known. But you can still describe it in words. A very simple example. A blimp decreased its height by 290.5 feet to get a new height which you know is 1,073.4 feet. But for some reason, perhaps because you forgot to measure it at that point, you forgot what the original height was. You merely knew how much I dropped, what it was after I dropped, and you ask, what was it beforehand? Well, in this case, common sense will tell you what to do without the algebra. But to use this as a vehicle to show you how algebra is going to work in the future with far more complicated situation, what we do is this. If we can describe what's happening and find the thing that we don't know, and that is the height before it dropped in this case, let a variable stand for its measure which we don't know. Now the question in algebra will simply become this. Can we say this verbal sentence in symbols? Well, it says that the height is decreased by, that's decreased in verbal form, 290.5, and the results of this is a new height of 1073.4. Now, if we can restate our verbal problem, our English sentence into a math sentence form, this gives us the freedom to forget what this even stands for. Our objective now is simply to solve an algebraic equation, in this case for the variable h, which means we wish to isolate it on one side of the equation by itself. And to do that, we don't look at the number we want to get rid of first. We look at what that number is doing. So our emphasis is on the doing symbols, the operation symbols. I want to undo subtraction. And of course I do that by adding, and of course the same amount. But the addition law of equality says I may add anything to one side if I add the same amount to the other. So this addition undoes that subtraction, isolating the variable, then doing whatever I was instructed to do on the other side, in this case adding two decimal numbers, I now recall what h stands for. It was my original height. So this is simply reading, look, your height is 1,363.9 feet. Now again, I want to emphasize this is so simple that in many cases you can easily see that I'm going to add this to this without having to go through an algebraic equation. We're simply using this as an opportunity to say this is the way things will work in more advanced math, when once you've got done saying it, it's so complicated you can't see what to do. But by writing it algebraically and learning the rules of algebra, you can isolate the unknown by following these rules and in fact find that item you wish to know. Now, in the future, the secret to working story problems will be to learn how to go from a verbal statement to a mathematical statement, and then at that point to solve that mathematical statement, which is nothing more than a symbol pushing game, which you're just beginning to learn the easy front edges of this game in this course. And in this course, just in our spare time, we're beginning to learn some of the rules for translating from English, from words into symbols. A number in English in algebra is simply a letter, a variable. If we have no reason to pick any other letter, quite frequently we'll pick on X or Y or Z. But if we have a reason like the last one to know that we're talking about tax, then let's call it a T. If we know we're talking about force, then let's call it F. So it's your choice of what you want to call it. So the word a number in algebra is simply a letter. The phrase decreased by in algebra is simply subtract. And of course, a number in English is still that number in math. And the verb is, or any form of its tenses, to be, was, could be, should be, is simply another way in algebra of saying equal. And a number is still a number. So a number decreased by 49.4 is 102.34. Now, to answer the phrase, what was that number in algebra, simply means solve the equation. So at this point, when we've gone from the story problem to an algebraic equation, it's not even important that we remember what x stood for. It's just a number, any number. And all we have to remember is that algebraically, or arithmetically really, to undo subtraction, we add the same amount. That's an arithmetic principle. And the algebra law says whatever you add to one side of the equation, that's fine, providing you add it to the other side of the equation. Now, addition undoes subtraction, isolating the variable, which is solving. But this lesson says to add the decimals. We line up the decimal points and the places, and then just add up the digits in like places. And we're done. Our number is 151.74. Isn't that quite simple? Now, of course, as you go on to more advanced math, the sentences become more complicated, and hence the algebraic equations become more complicated, or at least they seem so. But you'll find by that time it's simply the accumulation of a lot of simple rules like this. Just as learning the game of chess. No one movement rule of chess pieces are complicated. A complicated strategy is just combinations of very simple rules. And so it will be in algebra. So look forward to this in the course perhaps after this. That all algebra is learning a symbol pushing games, and of course in that game we're going to use arithmetic every time we turn around, which is why we're reviewing it in this course. Always remember that it is simply an extension of this basic idea which put man on the moon and now reaching for the stars. Once you're grounded in the basics that this course and the next course will teach you, you're on your way. This is your host, Bob Fennell, leaving you with, we hope, a very simple review lesson. We'll see you the next time.